You've stood on a boarding bridge, looked out the window, stared directly at the belly of a massive commercial airplane. And you probably noticed nothing unusual. But there's something hiding underneath every single commercial aircraft on Earth, something so small, most passengers walk right past it their entire lives. It's a tiny dent. A small recess pressed into the skin of the fuselage, right underneath the cockpit. And when you find out what it actually does, you will never board a plane the same way again. Balance scale and context. First, let's talk about what we're actually dealing with here. A Boeing 737 weighs around 80,000 kilograms fully loaded. That's the same as 50 adult elephants hurtling through the sky at 900 kilometers per hour, at 35,000 feet, where the outside temperature is minus 56 degrees Celsius. At those conditions, the air is so thin you'd lose consciousness in about 20 seconds without pressurization. And yet, every single system on that aircraft has to work perfectly, every single time. No margin for error. No, we'll fix it next flight. So when engineers put something on the outside of a plane, no matter how small, it's not decoration. It is never decoration. Historical backstory. Here's where it gets interesting. In the early days of commercial aviation, the 1950s and 60s, pilots had a problem. They were flying faster, higher, and in more extreme weather than anyone had ever attempted before. And they kept running into the same terrifying issue. Ice. Not just on the wings. Not just on the engines. On the sensors. You see, modern aircraft rely on a network of tiny probes and sensors embedded in the fuselage to measure everything: airspeed, altitude, angle of attack. These sensors feed data to the cockpit instruments. And the cockpit instruments are the only thing telling the pilots what the airplane is doing. If those sensors freeze, the pilots go blind. In 1974, a Northwest Airlines flight received completely incorrect speed data because of iced-over sensors. In 1996, a fatal crash in the Dominican Republic was caused by a blocked pitot tube, a sensor covered in insects from an overnight layover. Investigators began asking the same question. What if we could build a sensor that was virtually impossible to block, freeze, or fail? The answer was hiding in the shape of the aircraft itself. Core simplification. To understand what that tiny dent actually is, you need to understand one simple idea. Air pressure tells you everything. Think about it like this. Stick your hand out of a car window at highway speed, you feel pressure pushing against your palm. Now tilt your hand downward, you feel less pressure on the front face, more on the underside. Aircraft use this same principle. By measuring how pressure changes at different points on the fuselage, computers can calculate how fast the plane is moving, at what angle it's cutting through the air, whether it's about to stall. That tiny dent you saw? It's not a dent at all. It's a port. A pressure port. A precisely machined hole in the skin of the airplane. And it might be the most important hole in aviation. Magnifying glass tilted left. Deep explanation. Here's how it actually works, step by step. Imagine you're holding a garden hose with your thumb half over the opening. You can feel the pressure of the water building up behind your thumb, right? Now imagine instead of your thumb, it's a tiny, perfectly shaped recess in the side of an airplane, and instead of water, it's air. As the aircraft moves forward, air flows around the fuselage in predictable patterns. Engineers use that small recessed port to sample air at a very specific point on the aircraft's skin, a point where the pressure reading is clean, consistent, and unaffected by the engines or the turbulence off the wings. This is called a static port. And here's the clever part. The static port isn't measuring the air rushing past the airplane. It's measuring the ambient pressure of the air surrounding it, the still air, not the moving air. By comparing that static pressure reading to the pressure coming from the pitot tube, that little probe sticking out from the nose that does face directly into the wind, the onboard computers can calculate your airspeed to within a fraction of a knot. Pitot pressure minus static pressure equals dynamic pressure. Dynamic pressure equa.